Alright, so this lecture is about work and energy, and this is kind of an extension of what we were talking about in the last class about conservation of energy. Just kind of a recap, we said that according to conservation of energy, that the total energy contained in a closed system is constant, and although the energy can change from one form to another, the total energy content of the system, cannot change. But that is just for a closed system. And a closed system is one that cannot exchange work or heat with its surroundings. If you do allow work and heat to be exchanged, then it is possible to change the total energy content of the system. And so, for this screencast, we're going to consider work, and then later on in the course, when we get to thermodynamics, we'll see the role that that heat has to play in changing the total energy as well. But for today, we're just going to focus on work. So work, once again, is a way to change the energy of a system. It's a way for energy to leave the system. It's a way to add energy to that system. In physics, though, work has a very specific definition. A lot of people, when they hear the word work, they think of their job, or they think of like a lot of physical exertion. However, in physics, for a constant force being applied to an object, work will be defined as the force being applied to the object times the displacement of that object. Okay, so I'm going to use delta R for displacement. Okay, the displacement is in meters, the force is in newtons, and a newton meter is a joule. So work is measured in joules, which should tell you something right there because work and energy have the same unit. Okay, but the key thing here is that if there is no displacement, if delta R is equal to 0, it doesn't matter how much of a force you apply to an object in physics, the work done on the object would be 0. Okay, so keep that in mind. There actually has to be a displacement, in order for work to happen. The other very important thing is that when we calculate work, we only use the component of the applied force that is parallel to the displacement that occurs. Okay, so it's that component that's in the same or in the opposite direction from the displacement that's occurring. If there is no component of the force parallel to the displacement, then no work is done. So to kind of show you what that means, say that we have a box and we're pulling that box with some force, I'll call that F, and the displacement of that box, it moves, and the displacement will be in that direction. And say this force is being applied at an angle of theta. Okay, so we're going to make this very general. So the force is being applied at some angle theta. It's going to have two components. It's going to have this x component. It's going to have this y component. Only the x component of this force, which is parallel to the displacement of the object, will be used to calculate work. So in this case, what we would say is that the work would be equal to the force we're pulling it with, F, times the displacement that occurs. But then since we only need that parallel component, we would have a cosine theta term because F of x is equal to force times cosine of theta. Okay, so this equation right here is the most proper equation for a constant force being applied to an object, as it gets displaced. However, if that theta is equal to 0, in other words, if that force is parallel to the displacement already, then that equation just gets reduced to that first equation that I showed you. Okay. A situation that comes up sometimes, or that you'll be asked about, is, if an object is moving in a circle, like that, and it's attached to a string, and the centripetal force is being applied by something, but it's pointing towards the center, does that centripetal force do any work on it? So I'll let you ponder the answer to that. And it turns out that because the centripetal force, the displacement is in this direction, and the centripetal force is 90 degrees with respect to that, because there's no component of the centripetal force that's in the same direction as that displacement, we would say for this situation that no work is done. Okay, so no work is done on the object because there's no component of the force that's in the same direction is the displacement of the object moving in a circle. Okay, so keep that in mind. If you push like straight down an object, or even if it's swinging a circle, so it has a displacement, but that force is being constantly applied perpendicular to that displacement, then no work is being done on that object. Okay. The other thing that we have to watch out for when we talk about work or use work is that we get the sign right. And by sign, I mean the mathematical sign. Whether that work has a positive sign or whether that work has a negative sign. So the way I like to explain this is that work done by external conservative forces. The conservative forces, primarily are pushes and pulls. Okay, so work done by external conservative forces on a system, they increase the mechanical energy of the system. And by mechanical energy, I'm referring to the kinetic and or the potential energy of the system. Whereas work done on a system by conservative forces is defined as being positive work. Okay, so any work done by an external conservative force on the system, not by the system, but it's actually being put into that system. So you're pulling that box, you're compressing the gas, whatever. If work is being done on the system, then that will be considered to be positive work. Now, if work is done on a system by non-conservative forces, so that would be friction or air resistance, this causes the creation of thermal energy, which I hope you guys noticed in your activity. It causes the creation of thermal energy, and it causes a decrease in the mechanical energy of the system. Okay, and this is defined as negative work. A way that you can understand this is that friction and air resistance always act in the opposite direction from the displacement, okay, rather than the same direction. And therefore, it'll have a negative sign associated with, and then so it'll have negative work, and it'll decrease the mechanical energy of the system. But I want to make clear that although it decreases the mechanical energy, the total energy of the system can still be equal, okay, or rather is still the same. It just gets converted into thermal energy. Okay, these frictions and air resistances, very often they're contained within the system, and so they're not external forces. Okay, but they're not conservative forces either. Okay, and so they change mechanical energy from mechanical energy into thermal energy. So from this idea, we can write a new equation for the conservation of energy compared to what we did in last class. So we can now say that if we take the initial kinetic energy of a system plus the initial gravitational potential energy plus the external work done by conservative forces plus the work done by non-conservative forces, and remember, this will always be negative, okay, in this equation. All that has to equal the final kinetic energy plus the final gravitational potential energy that we have in our system. Okay, so this is the new equation that we'll be working with. And as far as analyzing physical systems in a physics problem, I'll show you how useful it can be to use this equation and to use this whole idea of work and energy. So let's zoom in a little bit here. We have a situation where we have a box, and this is going to be pulled up an inclined plane. I know how much you guys love inclined planes. So this is going to be pulled up an inclined plane, and it's going to be applied by a force of 100 Newton that points parallel to the incline. And there's also friction present in this case. Okay, and what we want to do is we want to calculate the change in kinetic energy of the box. In these problems, you want, rather than a free body diagram at this point, what you want to do is you want to sketch a before and after for the system. So this is going to be inclined at 30 degrees. The before part is down here. Okay. The after part will be up here. Okay, so here's after, here's before, and again, this is because we're worried about our initial and final state of the system. We don't really have to worry about kind of what happens in between as far as energy. Now we know it also gets displaced 20 meters. Okay, we know that that's going to result in some change of height h. We're going to make up the plane positive in this case. We know from the problem the weight, which is mass times gravity, the acceleration of gravity, is 80 newtons. Okay. We know that the applied force is 100 newtons. We know that our coefficient of friction is 0.220. Okay. And theta, 30 degrees, is already in there. 20 meters is already in there. Okay. So I think at this point, we are ready to go. If you want to, you could also calculate the mass. So that'll be 80 newtons divided by 9.80. So that gives us 8.16 kilograms in case we need that later on. Okay. Now for these problems, I want you to use this chart, and we're going to be using this bar chart to kind of track the energy and work in a visual way. And so as far as what the system here is, we'll have it be the box plus the Earth. So I'm going to include the Earth in my system for potential energy purposes, which means that we'll then have gravitational potential energy. Okay, the non-conservative forces that I have present is friction, so you just keep track and write these all down. And the external force would be the pull on the box. Okay? Alright, so as far as this chart and how you fill it out, you're going to use this as a bar chart, and you're going to track the energy in the system before and after. I know it's kind of hard to read because of these red lines, but this is non-conservative, and that says external. And so originally, I'm going to set my reference point to be the ground, okay, right here. So originally, I have no kinetic energy. It starts from rest. I have no potential energy because it's at the reference point. I know that I'm going to have some non-conservative work done by friction, so I'm going to make a little bar to indicate negative work. I also know that that force is going to, do external work, and so I'm going to have positive work, and probably more positive work than friction, so I'm going to make that bar a little bit bigger, happening to that. And what's going to happen is afterwards I'm going to have some amount of kinetic energy, and then notice because I'm pulling the box is going to end up above my reference point. I'm also going to end up with some potential energy as well. Okay, these don't have to be terribly accurate. Okay, but I would like to see you guys, keep track of what's positive, what's negative, and where's the energy at before and after. Okay. So we're going to first do the work calculation, figure out how much work is done by our external forces, and we're going to do a free body diagram. So the free body diagram, we have the 100 Newton force pulling it up. We also have the force of gravity, the weight pulling it down. And we've got this normal force, okay, between the inclined plane and that box. For the external work, okay, it's going to be fairly straightforward. Because the 100 newtons is parallel to the plane, parallel to the displacement, it'll simply be the 100 newtons force that we're applying times the 20 meters that we move it, so that'll be 2,000 joules. Okay. As far as the non-conservative work, okay, we're going to make it negative, and that'll be the force of friction times this displacement. So to get the force of friction, remember, this will be equal to mg cosine theta, okay, because we're on an inclined plane. This is the equation for this normal force, times mu, times the 20 meters. Okay, so we put that all together. We have negative 80 newtons times cosine of 30 degrees times 0.22. This is 0.220 times 20 meters. Okay, and you calculate all that, and when you do that, you would get negative 304.8 joules. Okay, so we have how much external work is done, and we have how much non-conservative work is done on it as well. And then we go back to this energy equation. We have, from that top bar graph here, we have non-conservative work plus external work is equal to final kinetic energy plus final gravitational potential energy. And now we plug in numbers and equations here. So I'm going to keep this as a variable because we want to know the change in kinetic energy. It starts off at 0, so the final kinetic energy would be the change in kinetic energy. For the non-conservative work, I have negative 304.8 joules plus 2,000 joules is equal to my final kinetic energy plus mgh. So we got to figure out what this h is. Looking up top, we see that we have 20 meters for our displacement. That's going to be angled at 30 degrees, and so we want to figure out what this h is. Okay, okay, this distance h is. So we can say h is going to be equal to 20 meters times, sine of 30 degrees, which is equal to 10 meters. And so down below here, we'll have negative 304.8 joules plus 2,000 joules is equal to final kinetic energy plus 80 newtons, again that's mg, times 10 meters. Okay. Our final kinetic energy, okay, then would be negative 304.8 joules plus 2,000 joules minus 800 joules. Okay, and you put all that together, we get our final kinetic energy is equal to 895 joules, and that is equal to the change in kinetic energy, which answers our question. So essentially what this is saying is that this external work that you put into it, some of it went into forming 304.8 joules of thermal energy. Some of it went into increasing the potential energy of the system. Okay, and what's left has to be the kinetic energy that the box has. And then if you were asked to find the velocity of that box, you could do that fairly easily as well. Okay, so once again, this conservation of energy idea is just another way to look at physics problems. Okay, and it provides an alternative a lot of times to the whole idea of having to use kinematics and forces in order to solve it. We still use forces, but now we use forces to calculate work, and we think about energy and work. All right, I hope this helps.